Dr. B here, and let's take a slightly more advanced look at NMR spectroscopy. We've got 6 samples here, and we're going to discuss what the NMR spectra would likely look like. One thing we're going to pay attention to is the symmetry of the molecules will make it so that there will be a certain number of overlapping peaks. We have to pay attention to that. Let's start with this bottom section here, which shows you where the peaks typically show up. If you've got hydrocarbons, they're typically at the right end of the spectrum. It's measured in parts per million. And so you have typically about 1 part per million for alkanes. If you have NH groups, they're still not that far down the spectrum. This is considered to be downfield. This is considered to be upfield. Notice that 0 is on the right. Alkenes can bring you all the way up to 5 parts per million. Ethers, more like 4 parts per million. If you have aromatic rings, they're typically in the 7 to 8 region. Amide hydrogens can be around 7 parts per million. The aldehyde hydrogen can be very diagnostic because it's all the way down at 9 or 10 parts per million, and carboxylic acids can be beyond 10, where there's not much else. What did we miss here? Alkanes might show up in the 3 or 4 region, and the hydrogens next to a carbonyl typically show up at about 2 parts per million. So memorize those and you get a good idea of what functional groups might be present. This sample here, this is known as neopentane, and if you look at it, CH3, 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 and nothing, no hydrogens there. So neighboring hydrogens for every single one is 0. Plus 1 gives rise to a signet, so each one gives rise to a 3H singlet. However, this molecule is 100% symmetrical, meaning that every hydrogen is in the same chemical environment, entirely overlapping, so you'd see one giant singlet at about 1 part per million for this molecule. This molecule, let's go through it piece by piece. This would be a 3H singlet, as with this one. They're pretty symmetrical, so I'd expect this to coincide almost exactly. This would be a 1H, nothing on that side, but 2 on that side, a 1H triplet. This would be a 2H, and that means the area of it is 2. And we have 1H on that and 3 on that. That makes 4, so this is a 2H pentet, and that's a 3H triplet due to the 2 neighboring hydrogens. Add 1 to get your triplet. This molecule is highly symmetrical down this region, so let's just cover one side of it and say that it's going to be duplicated. This would be a 3H singlet since there are no hydrogens there, and 3 hydrogens is the area of the peak. You'd get a smaller peak down here, somewhere in the aromatic region, 5 or 6 or 7, and that would be a doublet due to the 1 neighboring hydrogen. This peak here would give you a 1H triplet since it has 2 neighboring hydrogens. This one here would be a 1H singlet since it has no neighboring hydrogens. This 3H singlet would be completely overlapped with that one, so it would look right on top of it. This one overlaps with that one. That one does not overlap with that one because they're in a slightly different environment. Here we have a 2H singlet. However, since this cannot rotate, each one of those hydrogens might show up in a separate environment. This is a 3H singlet. This is a 2H triplet. This is a 2H. Check that one out. 3 and 2 is 5 neighboring hydrogens. That's a 2H hextet. And that is a 3H triplet. Very symmetrical, so we'll see a lot of overlap here for the 3H singlet, for the 1H doublet, and this 1H doublet, and that's about it. This one's going to overlap with that one. That one's going to coincide with that one. That's going to coincide with that one, and you'll get a lot of symmetry there. Cyclohexene also has a lot of symmetry along this plane right here. So I'll wrap it around the horn, and then we'll talk about the ones that coincide. 1H, quartet. 1H, 2H, 1, 2, 3 quartet, 2H pentet, 2H pentet, 2H 1 plus 3 quartet. Since these things are relatively rigid and cannot rotate, you might see some splitting within it. In other words, not to complicate matters too much, but this hydrogen on top would be a little bit different than the hydrogen on the bottom, so you might get some fine structure depending on the power of your instrument. But which peaks coincide? This one with that one with that one with that one, and that's cyclohexene. They chose examples that have lots and lots of symmetry, which can be complicating. That's a more advanced look at NMR spectroscopy.